So last time we were talking about anticlines and synclines. Well, mostly I was talking. The rest of you were sitting around watching. Anyway, let's move on with domes and basins. Now, in the case of both domes and basins, strata exposed at the surface form concentric circles around the central point. But there are some notable differences between these two structures. For one thing, a dome is an anticlinal structure where the flanking strata encircle the central point and dip away from it in all directions. Now, because a dome is basically an anticline, a closed anticline, it should follow the same rules as anticlines in general. For example, recall last time that the oldest strata in anticlines tends to occur along the hinge line. And so too in the case of domes, the oldest strata occurs at the central point and become progressively younger, moving away from the central point so that the youngest strata occur right along the margins. And if we take cutaway views, cross-sections of the dome, we see indeed that regardless of how we slice this particular structure, it shows a anticline below the surface. We can also express this structure in terms of strike dip symbols. If you look closely at this illustration, we find again that the strike portion of the strike dip symbol tends to parallel the contacts between adjacent strata. And since the strata dip away from the central point in all directions, we would expect the dip portion of the strike dip symbols to also point away from that central point. And here's another perspective of a dome. Again, we see that the oldest formation exposed on the surface occurs right at the center, and the formations become progressively younger as we move away from that central point. And again, cross-sections show an anticlinal structure. And what's more, if you remember in the case of anticlines, that strata in anticlines tend to dip away from the hinge line. So too in the case of a dome, the strata dip away from the central point. Here's a aerial view of one particular dome. This is the Sinclair Dome in Wyoming. And not knowing the ages of the strata in detail, we can right away assume that the strata in the center is the oldest, and what's more, the strata become progressively younger away from the center. And if you look real closely at the photograph too, particularly in the foreground, we can see that the dipping strata tend to all dip away from that central region. As we move away from that domal structure towards the flanks, notice that along the flanks we basically have a overall anticline. Another example is the Black Hills of South Dakota. Here, for an example, we're going to look at this profile XY shown as a line in the upper figure. And basically what this profile represents is a cross-section shown in the lower left. It's like taking a slice through the structure in the upper view and then turning that slice sideways to 90 degrees so that we look at an overall cross-section. And in the cross section, again, we're looking at the profile X to Y going from left to right. But again, the rules of a dome basically follow here. The granites and the schists are the oldest rocks within the Black Hills, and they occur within the central part of the structure. And as we move away towards the margins, particularly along these horizontal dipping flanks, these are the younger rock units within this overall region. What famous landmark occurs in the Black Hills? Anybody know? Yeah, but what's the landmark? Mount Rushmore. Mount Rushmore is carved within the ancient granites within the central part of the Black Hills. Now, a basin, on the other hand, is a synclinal structure appearing as a bowl-shaped depression where rock layers dip towards a central point in all directions. And notice that in cross-section, regardless of how we slice through the basin, we do see a synclinal form occurring below the surface. And because basins are synclinal structures, they also follow the rules of synclines. Recall last time that the youngest strata tend to occur along the hinge line of a syncline. And so too, in the case of basins, the youngest strata or formation occur around the central region. And the strata become progressively older as we move away from the center, so that the oldest formations that are exposed on the surface tend to occur along the margins of this particular block diagram. And again, if we look at the cross sections, regardless of how we slice through the basin, you're going to get a synclinal structure below the surface. And recall also in the case of synclines that the limbs of a syncline dip towards the hinge line. So too in the case of the basin, the strata dip towards that central point. A good example of a large basin is the Michigan Basin, which underlies the entire state of Michigan. And like before, let's take a line of profiles, say from A to B in the upper figure, and cut and slice through that line and turn it 90 degrees to get a cross section, as shown in the lower left. And in the cross section, again, we find the profile A to B and going from left to right. The different colors of the formations in turn represent different ages, and those colors are explained in the key in the upper left-hand corner. And the terms Pennsylvanian, Mississippian, Devonian, Silurian, Ordovician, these are geologic periods in the geologic time scale. And by convention, the oldest period within this region, the Ordovician, occurs at the bottom, and the different periods like Silurian, Devonian become progressively younger as we move up the key, so that within this area, the upper Pennsylvanian represents the youngest strata. So let's compare these color codes with the actual map, and what we find is that the youngest strata, the upper Pennsylvanian strata, occur at the center of the Michigan Basin. And in the lower left-hand corner, notice that in the cross-section, the arrow points to the youngest strata. We can just use the principle of superposition to convince ourselves that the brown is indeed the youngest rocks of all of these different sequences. And as we move away from the center, the strata become progressively older. For example, the red represents the lower Mississippian rocks. And then the oldest strata occur right along the margins of the basin, as indicated by the arrows in the cross-section. And those rocks are Ordovician in age. So indeed, the Michigan Basin does follow the general rules of basins. Of course, you don't see this large structure on the surface because it's all covered with younger rocks and vegetation, things of that nature. But what we see here is a geologic map, which is what the surface would look like if all the trees and vegetation and soil were removed and we were just simply looking at the bedrock exposed on the surface. Any questions? Now, we saw before, last time we defined the different parts of a fold. For example, we found that the axial plane is an imaginary plane that divides a fold into two symmetrical halves, so that in cross-section or cutaway view, one side of the axial plane is the mirror image of the other side. And what's more, the hinge line is defined where the axial plane intersects the folded strata. What else does the hinge line define? We can give a hinge line a compass direction, like north-south, north 30 degrees east. And what exactly is the hinge line defining in terms of the fold? Yeah, the direction or the strike of the fold. And so oftentimes geologic maps will have the hinge line marked as an indicator of the direction or the strike of the folds that are depicted in the area of the geologic map. And obviously we're looking at an anticlinal structure where the limbs dip away from the hinge line or fold axis. The hinge line and fold axis are synonymous, so sometimes you'll get the term fold axis, other times hinge line, but those two terms mean the same thing. Now, a non-plunging fold is when the hinge line is horizontal. And notice that in this particular figure, after erosion, we have strata on both sides of the axial plane, which essentially parallel the axial plane. And this occurs if the fold is horizontal and does not plunge. And here's another example of a non-plunging anticline. Again, the hinge line is horizontal in the non-plunging fold by definition. And as a result, if the hinge line is horizontal, then it parallels the ground surface. And we can readily see this on the map view, the surface view, where these ridges are basically parallel to the overall hinge line. In particular, the anticline appears as a linear ridge in the case of a non-plunging fold. However, things get complicated if the fold is plunging. By definition, a plunging fold occurs when the hinge line is not horizontal and the fold appears to be plunging into the ground. And here we see in this illustration a couple of examples of non-plunging folds. Notice in the figure on the left before erosion that if you look at the axial plane, we have the upper arrow indicating the horizontal, and the actual hinge line is occurring at an angle to that horizontal. And that angle is from the horizontal is referred to as the plunge of the overall hinge line. And if we erode away the upper part of the plunging anticline, notice that on surface view we get this kind of a horseshoe pattern or a hairpin pattern exhibited by the strata on the surface. And this is a characteristic of plunging folds as viewed on geologic maps, and we'll take a look at this in more detail. So in the case of plunging folds, whether it's a plunging anticline or a plunging syncline, the hinge line itself is inclined at an angle to the horizontal. And if the hinge line is not horizontal, then the structure is referred to as a plunging fold. And what's more, the fold on surface view takes on the horseshoe or a hairpin pattern on the ground surface. And we're going to look at this pattern in a little bit more detail. But as we saw before, when folds plunge into the earth, the curved strata form a horseshoe or hairpin pattern on the surface. Now, in the case of anticlines, the horseshoe or hairpin pattern will close in the direction of plunge, whereas in the syncline, it'll be just the opposite. The horseshoe or hairpin pattern will open in the direction of plunge. So let's say, for an example, in this upper block diagram, before erosion, we have this imaginary horizontal plane plunging through the, kind of passing through both the plunging anticlines and plunging synclines. So we have two plunging anticlines, and in between we have a plunging syncline. But in all cases, the plunge is in the same direction as indicated by these arrows shown on the surface. Now what we're going to do is erode away the upper part of these plunging folds down to this horizontal plane. And when we do that, notice that we take on these hairpin patterns on the surface. Now, by definition, in the case of anticlines, notice that the horseshoe pattern closes in the direction of plunge, in this case in the direction that these purple arrows are pointing, whereas in the case of syncline, the horseshoe pattern opens up in the direction of plunge. Yeah, the purple directions are showing the direction that the folds are plunging into the ground. Yeah, the horizontal plane in the upper diagram, what we've done is eroded the upper parts of the folds down to that horizontal plane and removed the plane, so that now in the lower diagram we're looking at the resulting structures after erosion as they appear on the surface. Maybe I'll answer your question. But here, for an example, is a doubly plunging anticline. In other words, it's plunging in two directions. And so if you look at the structure, again, we're following the rules of anticlines. The hinge line is right through the center. Notice that peak running right down the center. That follows the hinge line of the anticline, right along the core. And we would expect the oldest strata to occur right along that hinge line. And the strata then will become progressively younger as we move away in both directions from the hinge line. But because this anticline is doubly plunging, well, first of all, the strata is also going to dip away in opposite directions from the hinge line. Now, because the anticline is doubly plunging, we have a horseshoe pattern both in the foreground and also in the background that closes. Okay? Does everybody see this? Here's another example. These are plunging anticlines and synclines in the Appalachian Mountains in Pennsylvania, I think near Harrisburg, Pennsylvania. But notice that in the foreground we have a plunging anticline. For example, we can follow this particular resistant rock layer and watch how it forms this hairpin pattern, bends around and comes back in the other direction. So this is the central, this is the hinge line of that particular plunging anticline. This ridge that follows this mouse arrow. In the background, we horseshoe pattern. If you just follow this resistant rock layer, it towards the right, it bends, it wraps around, and goes back in the opposite direction. Okay. So which direction are the folds plunging? Keeping in mind our rules of how hairpin patterns open or close in the direction of plunge. Are these folds plunging towards the upper left-hand corner or towards the lower right-hand corner? Yeah. The folds are plunging towards the upper left-hand corner. How do we know this? Well, we know this is a plunging syncline, and notice that the hairpin pattern opens up towards the towards the upper left-hand corner. In the foreground, we have a plunging anticline, and by definition, the horseshoe pattern closes in the direction of plunge for the anticline, and indeed it does close towards the upper left-hand corner. So this is how we know that the plunge is towards the upper left-hand corner. Again, you look like my computer when it freezes. I get no emotions or no. Any questions on this? This is cool stuff. I mean, this is geology. Did I answer your question? No? It's kind of hard to visualize exactly what's going on here. If you can't conceptualize in your mind, don't worry about it too much. Just know that plunging synclines open up in the direction of plunge, whereas plunging anticlines close in the direction of plunge. And if you just keep those rules in mind, you should be okay. Now, folds can have different degrees of symmetry or asymmetry. First of all, let's look at what are called symmetrical folds. In symmetrical folds, the axial plane is vertical, and beds dip at about the same angle but in opposite directions on both sides of the axial plane. For example, in the lower figure, if we were to measure the angle of dip for the limb to the left and also for the limb to the right, those angles should be equal. On the other hand, the limbs are dipping away from the axial plane in opposite directions at the same angle, and this by definition is a symmetrical fold. And here's a symmetrical syncline. Again, if you look at the synclinal structure, in the case of synclines, the limbs dip towards the axial plane, and in this case, the dipping limbs should be dipping towards the axial plane at the same angle of dip. Now, in the case of an asymmetrical fold, notice that the axial plane is inclined the limbs are still dipping in opposite directions, but the dip angles are different. One limb is dipping at a steeper angle from the other limb, even though the dip angle, even though the limbs are still dipping in opposite directions. And we have a picture of an asymmetrical anticline and syncline shown in the upper right-hand corner. Now, eventually, the fold can overturn or flip onto its side, and in that case, we have what's called an overturned fold. Here, the axial plane is steeply inclined at an even greater angle than in the case of an asymmetrical fold. But now what's different is that both limbs dip in the same direction, but at different angles. It's just that one limb is dipping more steeply than the opposite limb. But if you look at the lower figure and compare the two limbs and look closely, they're both dipping in the same direction towards the left. So what happened was that the symmetrical fold, as it started to bend over, became asymmetrical, and then eventually flipped over towards to the point that it actually overturned upon itself. And as the fold continues to turn over, eventually it lays down onto a horizontal plane where the axial plane is horizontal, in which case it then becomes what's known as a recumbent fold. So the greater the asymmetry, the more intense the deformation. And as we see in this figure, the direction of greater intensity of folding is towards the right. So if we start at the left with a symmetrical fold, as we go towards the right, towards greater intensity of folding, we go progressively from a symmetrical to an asymmetrical, and then to overturned, and then finally at the far right hand corner we encounter recumbent folds. Any questions? So if you get a illustration of the axial plane and the limbs, just by looking at the picture, you should be able to define whether it's an asymmetrical, a symmetrical, or overturned, or recumbent. You got 4 choices. Now here's a complicated fold. This is the axial plane of an overturned fold, and this is a huge fold. Notice that at the very bottom we have a couple of vans for scale. But again, the axial plane is passing in and out of the screen. Here's the line of intersection of the axial plane. And if you compare both sides of the plane, we see that one side of the axial plane is the mirror image of the other side. This is a very complex structure. I think this picture was taken in Israel, if I recall. I think it happened with the parting of the Red Sea, but I'm not sure. Our favorite slide. That means that we're at the end of this lecture. Okay.